Have you ever wondered how scientists actually write down the story of a rusty nail, or a baking cake, or even a massive explosion? Well, they use this kind of universal language to describe all that change. And today, we're going to decode that language, chemical equations. Try to think of them less like scary, complex formulas and more like the essential recipes for how everything in the universe happens.
You remember that classic science fair experiment, right? The one with the baking soda and vinegar that makes a fizzing little volcano? Yep, that's a chemical reaction. And just like a recipe tells you exactly what to mix together and what you're going to get in the end, a chemical equation does the exact same thing for, well, for everything.
All right, let's dive right in. We are going to deconstruct this language of chemistry. We're going to break it down into its basic parts, and I promise, by the end of this, you'll be able to look at one of these recipes and actually understand the story it's telling. So, at its absolute core, a chemical equation is really just a form of shorthand. It's a super efficient way to show what you started with, we call those the reactants, and what you ended up with, those are the products, after some kind of chemical change went down. It's basically the before and after photo of matter.
Okay, let's use a real-world example, something we've all seen, the flame on a gas stove. This equation right here, it describes what happens when you burn natural gas. Now, it might look a little intimidating with all the letters and numbers, but don't worry. We're about to see that it's really just a simple story of ingredients turning into a finished product. First things first, let's talk about the reactants. These are your ingredients, the stuff you're putting into the reaction. You will always find them on the left side of that arrow. So for our gas stove flame, our ingredients are methane, the gas coming from the pipe, and oxygen, which is just all around us in the air. And on the other side of that arrow, we've got the products. This is the final dish, what you've created. When we burn methane, we end up producing two main things: carbon dioxide, which you can't see, and water, which is actually released as steam.
Okay, now what about those big numbers out in front? Those are called coefficients, and they're probably the most important part of the recipe. They tell us the proportions. In our flame example, this equation is telling us that for every single molecule of methane, we need exactly 2 molecules of oxygen. If you don't have that ratio, the reaction just won't work right.
But here's the thing. You can't just throw any old numbers in front of these chemicals to make a recipe. Nope. Every single chemical equation has to follow a fundamental law of the universe. It has to be balanced.
And this all comes down to one absolutely crucial rule: the law of conservation of matter. It's a fancy way of saying that in any chemical reaction, you can't just create atoms out of thin air and you can't make them disappear. They just get rearranged. So whatever you start with on the left, you have to end with the same number of atoms on the right.
So how do we make sure everything balances out? Well, the most common way is something called balancing by inspection, which honestly is just a smart way of saying trial and error. But the most important rule here, the one you can never break, is number 3. You can never change the small subscript numbers. Why? Because that would change the actual ingredient. It'd be like changing H2O, water, to H2O2, which is hydrogen peroxide, a totally different and much more dangerous substance.
And here's the proof. Let's do a quick atom inventory. As you can see in the table, on the left side, we start with 1 carbon atom, 4 hydrogen atoms, and 4 oxygen atoms. And on the right side, we end up with, you guessed it, 1 carbon, 4 hydrogens, and 4 oxygens. It's a perfect match. The story adds up.
So now that we know how to read these equations, let's look at the common types of stories they tell. It turns out that most reactions follow one of about 5 basic plots. It's almost like movie genres, and once you can spot the genre, you have a pretty good idea of what's going to happen. First up, we have synthesis. This is your classic coming together story. You start with 2 or more simple things, and they combine to form one single, more complex thing. A plus B makes AB. Simple as that.
A really simple example is just burning a piece of carbon, like charcoal. The solid carbon combines with oxygen gas right out of the air, and together they synthesize one new product, carbon dioxide gas. Now, the total opposite of synthesis is decomposition. This is the breakup story. You start with one complex compound, and something causes it to break down into 2 or more simpler pieces, so AB becomes A and B. And a perfect example of this is when you run electricity through water. That one compound, H2O, decomposes and splits apart into 2 much simpler substances, hydrogen gas and oxygen gas. The other 3 genres are just as easy to spot.
In a single replacement reaction, it's like one element cuts in and steals another one's partner. For double replacement, two couples just swap partners, like dancers on a dance floor. And finally, there's combustion. That's any reaction where something burns really fast with oxygen to produce heat and light, just like our methane flame from the beginning.
But hold on, there's actually another layer to every single one of these chemical stories: energy. You see, every reaction either releases energy into the world or pulls energy in from its surroundings. This adds a really cool, energetic twist to the plot.
And these two twists are called endothermic and exothermic. Endothermic reactions pull heat in. That's why those chemical cold packs you snap feel cold to the touch. But exothermic reactions push heat out. That's why a fire feels hot. It's releasing a ton of energy. So photosynthesis is endothermic. It's absorbing the sun's energy, while an explosion is just a really, really fast exothermic reaction.
Okay, for our final act, we're going to get a little more advanced. A ton of reactions happen in water, where compounds often break apart into these little charged particles called ions. And to see the real story, the true action, we need to look at what these ions are up to.
So this is what a typical equation might look like on paper. It just shows the whole compounds. And see those little letters in parentheses? AQ means it's dissolved in water, and S means it's a solid. So what's happening here is we're mixing two clear liquids, and all of a sudden a solid material appears out of nowhere. But what's really going on?
Well, to see the full picture, we write out what's called a complete ionic equation. This shows every single ion that's actually just floating around in the water. But if you look closely, you'll see some of them, like the calcium and the nitrate ions, are on both sides of the arrow. They didn't change at all. They're just kind of watching from the sidelines. So we call them spectator ions.
And if we get rid of those spectators, we finally reveal the net ionic equation. And this is the heart of the story. This is the main event. All that really happened in that whole mixture was a silver ion and a chloride ion found each other, locked together, and formed a solid. That was the real transformation.
So from the rust on a car to the bread rising in your oven, chemical equations are the stories of matter, and they are constantly happening all around us. The only real question is, now that you know the language, what reaction will you notice next?